So just for the sake of the video, we'll go back here briefly. A function f from D to R is called one-to-one or injective when for every domain elements A and B, f of A equals f of B implies A is equal to B. In other words, fa equals f of B only when A is equal to B. So here we want to consider this function from the real numbers minus -1, right? This one's not defined at -1 because you'd be dividing by 0. From the real numbers minus -1 to the real numbers given by fx equals 3x minus 2 over x plus 1. Show that f is injective. Okay, so we have to show that this is satisfied. fa equals fb implies a is equal to b. So it's an implication statement. P implies q. The first sentence of the proof of any implication statement, there's only 3 possibilities. Only 3 possibilities for a proof. If the proof doesn't start with one of these 3 possibilities, then, it can't be correct. Unless it's somehow understood that one of those 3 possibilities.
For the first sentence, you assume P is correct. So
yeah, assume P is true. Yeah, for a direct proof.
A.
So assume P is true. So that's the first sentence. Or assume Q not, or Q is false. That's if you're doing the contrapositive, because this is logically equivalent to Q not implies P not. So assume Q is false. In other words, Q not is true. So when you're trying to prove an implication statement, your first sentence is this, or this, or, by way of contradiction, assume P and Q not. One of 3 sentences. All right. So on the exam, I didn't see this sort of thing reflected, like when we were talking about show that this is a subset of that, or this is a subset of that, which is essentially an implication statement. I wasn't seeing this kind of thing reflected. Okay, there's certain templates. I mean, these are very vague templates, but there are certain templates one needs to follow. Okay, this is this is one of them here. Okay, so I mean, if your proof just doesn't fit into that template, it can't be right. No matter what. No matter what sort of clever things are written after that, it's not right, because you're just not fitting into a certain template. All right, so okay, so let's do this. Let's do direct proof. So what do I write? Assume P is true. There's no P here. I'm trying to show that this is P. This is P. This is Q.
Assume that f of A equals f of B.
That's it. Assume that f of A equals f of B. And then argue down to A equals B. So assume that f of A is equal to f of B. So now, what's f of A? What's f of A? What's f of A? Okay, so go back to
3A minus 2 over A plus 1.
Go to pre-calc mode. Go to pre-calculus mode now. Okay, now that we've done the template, go to pre-calculus mode. 3A minus 2 over a plus 1 equals what's f of b?
3b minus 2
over
b minus or b plus 1.
b plus 1. Yeah. So now what can we do here? Cross multiply, right? 3a minus 2 times b plus 1 is 3b minus 2 times a plus 1. So we can multiply it out here. 3ab minus 2b. Let's get some more space here. 3ab minus 2b plus 3a minus 2 equals 3ab minus 2a plus 3b minus 2. So, right, cancel, 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 cancel. Minus 2b plus 3a equals minus 2a plus 3b. Right? Add 2a to each side and 2b to each side. Right? And we get 5a equals 5b. So a is equal to b. I'm just doing algebra there. No explanations are necessary. Other than, just using the rules of ordinary algebra of real numbers. All right, that's what we wanted. As required. All right, we started with the assumption that a is equal to b, or fa is equal to f of b, and using that, we argued down to a is equal to b. And so that is an injective function. What's another way to show that that's injective? Right? Why is the f of x equal to x cubed injective? I mean, from the graph, why do you know that this function is injective from the graph?
Because it passes the horizontal line
Yeah, it
test.
passes the horizontal line test, right? Another way you would know that this is injective is to look at the graph, right? What's the graph of that thing look like? Well, it's got a vertical asymptote at -1, horizontal asymptote at 3, and other than that, it looks like this. Right? Passes the horizontal line test. Every horizontal line intersects that graph, and at most 1 point. As a matter of fact, every horizontal line intersects at exactly 1 point, except for this one right here, which doesn't intersect at all. All right, so let me write that down. All right, the graph of the function. Oops. The graph of the function y equals what was it? 3x minus 2 passes the horizontal line test. Why does the horizontal line test mean anything here? Why does the horizontal line test tell you your function is 1 to 1? Where does it hit that? That's 3/2, yeah. Or 2/3. No, wait. Equals it 2/3. Wait a minute. What did I do? Oh, sorry, that's not the graph. This is the graph. And so for x bigger than -1, this is positive. The horizontal asymptote at 3, vertical asymptote at -1, and then x-intercept at 2/3. Y-intercept at
-2.
So this is equal to. Oh no, -2. No, that's the y-intercept. That's right. I had it right before. Why does the horizontal line test actually say something? What's the deal? Wait. If y is equal to 0, that's where it crosses the x-axis. So that's 2/3. That's over here.
Maybe they're both below 3.
And then when x is equal to 0, this is at -2. This is it. Well, and then here it's up there. All right. I think I got it right now. All right. Why does the horizontal line test mean anything, though? I mean, why is it that a horizontal line intersecting the graph at most one time tells you that you're 1 to 1? A horizontal line corresponds to what?
The y.
It corresponds to the range element, the y. And that says that there's only one domain element that hits that particular range element. Okay? So on the homework, the first problem is the same thing here. Well, I mean, you have to show it's a bijection, so it's 1 to 1 and onto. And I'll explain what onto is in a moment. So, you know, you would have to say why the horizontal line test means something. Or just do the algebraic proof. I think the algebraic proof's a little more simple. Okay? All right, so that's 1 to 1. Let's go to the, or injectivity. Let's go to the next thing. A function from domain to range is said to be surjective or onto when the image of f is the entire range. When the image of f is the entire range. That is, another way to say it, for every b in the range, there is x in the domain such that f of x is equal to b. For every range element, there is a domain element that goes to that range element via f. So in these pictures up here that I was drawing, such a function like this is not surjective because there are range elements that don't have arrows coming into them. So here's a domain, here's a range. 1, 2, 3, 4, 5, 6, 2, 3, 4, 5. So if you've got something like that, this is not surjective because f of x is not equal to, so I'll label those elements, call this one A, this one B, this is C, is not equal to A for any x in the domain. Right? That is, A is not in the image of f. The image of f is, this element, this element, this element. So maybe we'll give those some names: A, B, C, D, E, F. So A is not in the image of f, which is, I guess I shouldn't use f twice, should I? D, E, F, G. A is not in the image of f, which is D, E, G. Or the image of f, which is D, E, G, is not equal to the range entirely, which is the set A, B, C, D, E, G. Here, if I had a function that looked like this, so if I just didn't have, oops, not the blue ones, the red ones. This function here is surjective. This one is not surjective, is surjective. So, the fancy word is surjective, the less fancy word is onto. Unfortunately, the less fancy word doesn't fit too well. So it's not used too much. Surjective is what's used more often. With injective functions, the term injective and the term one-to-one are used interchangeably. One-to-one is a good description. Onto is kind of awkward, so it's really not used very much. Okay, so there's the basic idea right there. And, well, let's do some examples other than those. How about that Moebius function we were just looking at? So show that f from the real numbers minus -1 to the real numbers minus 3 defined by f of x equal to 3x minus 2 over x plus 1 is surjective. Show that this function is surjective. Okay. The definition of being surjective is not an implication. It is not an implication. It is an existence statement. It is a statement of existence. All right, so here is the definition. For every b in the range, there is x in the domain such that f of x is equal to b. That is the definition of f being surjective. For every b in the range, there is x in the domain such that f of x is equal to b. For every bee, there is a flower that he likes. For every bee, there is a flower that he likes. How could you show me that that statement is true? For every bee, there is a flower that he likes. How does one prove a statement of that sort? It starts with a universal quantifier. For every bee, something exists. For every bee, something exists. That thing that exists is a flower that he likes. For every range element, there is a domain element such that f of x is that domain goes to that range. How do you prove something of that sort? What do I have to pick to start out with?
You would pick a random bee and prove that there is a flower it likes.
Pick a random universal thing. So for every bee, there is a flower that he likes. Pick some random bee. Pick some archetypical bee. The term that's often used is pick an arbitrary bee. Pick a bee arbitrarily. You don't know anything special about this bee. Just choose an arbitrary bee. Okay, so it starts out like this. So a proof of such a statement. So a proof of for every x there exists a y, pxy begins with the statement over D, over domain D. Let X in D be arbitrary. Let X and D be arbitrarily chosen. Okay, so anytime you're trying to prove for every X there exists a Y satisfying Pxy over domain D, it begins with the statement, let X be arbitrarily chosen, or something of that sort. Okay, so consider an arbitrary B in the set of real numbers minus 3. So it's just some real number, just not 3. Some real number other than 3. Could be 0. What do we need? What do we need for B? We must find some real number X such that what? Such that what? We've chosen a B, and we must find a flower that he likes. Here's a B. Oh, this B, he likes roses. Great. Here's a B. Oh, this B, he likes daisy. Great. What do we need to do here?
We need to show that f of x equals b.
Yeah. We must find some real number X such that f of X is equal to B. All right. That is, well, what's f of X? It's 3x minus 2 over x plus 1 is equal to B. That is, 3x minus 2 equals B times x plus 1. 3x minus 2 equals bx plus b. Right? 3x minus bx equals b plus 2. That is, so we need to find x such that f of x is equal to b. That is, we need to find x satisfying this. That is, x satisfying that. That is, x satisfying this. So x times 3 minus b. X equal to b plus 2 over 3 minus b. Are we done? Does that work? Does that work? Did I find x? We're given b. B is a known thing. It's a real number. It's known. I don't know what it is, but it's a known real number, arbitrarily chosen from the set of all real numbers. Now I need to find x such that 3x minus 2 over x plus 1 equals b. And now I've found that x is equal to this. Does that do the trick for me? Does that tell me what x is?
I mean, it does as long as b isn't 3.
Yeah, and because b isn't 3, that's fine. All right? Which is a real number of the domain because b is not equal to 3. Right? The range was the real numbers except for 3. So we picked an arbitrary real number that's not 3. And then we did all this algebra here, and we came out with x is equal to b plus 2 over 3 minus b. And that's a real number because b isn't 3. If b was 3, then there'd be a problem, but it's not. Okay? So that function is both injective and surjective. So when a function is injective and surjective, we have what's known as the following. So a function f from domain to range is called a bijection, or is bijective. Is called a bijection, right? Or is bijective, that's the adjective form, when f is injective, 1-to-1, and, not or, and surjective, 1-2. So 1-to-1 and onto. So for example, going back to the definition of a set A being countable is that there exists a bijection f from A to the positive integers. Okay, there's a labeling of the set with the positive integers 1, 2, 3, 4, 5, or the natural numbers, whatever you like better. If you like starting at 0, 1, 2, 3, 4, 5. That's what it means for a set to be countable. Okay, so in fancier terminology, it means there's a bijection between f and the positive integers. And of course, that function that we were just looking at there, f from the real numbers minus -1 to the real numbers minus +3, defined by f of x equal to 3x minus 2 over x plus 1 is a bijection. Okay? When you've got a bijection, y'all seeing the screen or freeze up? It's frozen with me. Let me redo it. How's that? Can you see me moving my pen there? Okay. When you have a bijection, you have an inverse function. Given a bijection, f from domain to range, there exists a function f inverse from the range to the domain, right, such that f of f inverse of x is equal to x, and f inverse of f of x is equal to x. All right, this is called the inverse function, a unique. So this is the only time inverse functions exist. Frozen again, huh? Is there some way I can reset my connection? So, for example, if this is the domain and this is the range, if you only have finitely many elements in the domain, then in the range, you're going to have exactly 5 elements, A, B, C, D, E. If we say 1 goes to A, 2 goes to C, 3 to B, 4, 5 goes to E, like that. If this is F, so given F as shown, right, F inverse is obtained just by reversing the arrows. So this is F, so F inverse just goes the other way around, and the arrows, F inverse of A is 1, F inverse of B is 3, F inverse of C is 2, D is 4, E is 5. Okay, so now when you compose functions, you get the F composed with F inverse, and F inverse composed with F is the identity. Okay. Consider the following statement here. Consider finite sets D and R with the same order. Let F be a function from D to R. The following statements are all logically equivalent. One, F is a bijection. What was the definition of bijection again?
Being both surjective and injective.
Yeah, F is surjective and F is injective. But with not or, and. F is injective and surjective.
Oh, sorry,
So-
I meant and.
Yeah, and you said and. You did, you said and. But with finite sets, it can be replaced by or. So F is an injection for finite sets of the same size, domains and range. 3, F is a surjection. So the following statements are logically equivalent. So if the domain and the range are the same size, then F is surjective and injective if and only if F is injective. F is injective and surjective if and only if, F is bijective and surjective if and only if F is just surjective. And F is injective if and only if F is surjective. When the domain and range have the same size. If they don't have the same size, then you actually can't have a bijection. You can only have one, an injection or a surjection, depending or neither, depending on the size of D and R. Okay, what does it mean to say the following statements are all logically equivalent? Okay, so before we prove this, okay, but before we do, what does it mean to say that 3 or more statements are logically equivalent? So let's explain with 3 statements. 3 statements, P, Q, and R, are logically equivalent when, well, P is logically equivalent to Q, Q is logically equivalent to R, and R is logically equivalent to P. Right? And remember that A is logically equivalent to B if and only if A implies B and B implies A. It's a double implication. It's a double implication. Right, so 3 statements. P, Q, and R are logically equivalent when, right, the following are all true. So we'll put them in a triangle, P, Q, R. So P implies Q, Q implies P, R implies Q, Q implies R implies P, P implies R. But do we need to prove 6 implication statements? Or is there a smaller set that we can prove? Well, actually you only need 3 or 4. Okay, but we're out of time for now. We'll talk about that next time. All right, so everybody have a good weekend. Like I said, I'll post the solutions to the exam. I'm just looking for one more student who needs to take it. Okay, so we'll see you on Monday, and that's all. Okay, all right, guys, have a good weekend.